In this video, we are going to look at the Lewis structures of covalent compounds. Now, a Lewis structure is a model, and these models show how valence electrons are shared within a molecule. A molecule is composed of atoms, and these atoms use covalent bonds. So they're held together by sharing of electrons, and you get the atomic orbitals that overlap. That's how the electrons are shared. A lone pair is a pair of electrons that is on a single atom, and a bonding pair is a pair of electrons that's going to be shared between two atoms. Another way of thinking of a bonding pair, this is a bond. If we look at an example, let's look at the electrons in F2. So this is what the Lewis structure of F2 looks like. All of these electrons here are lone pair electrons. So LPE or LP, either way, lone pair electrons, those are on the individual fluorine atoms. So they're not being shared between the two atoms, they're just on that localized atom. The bonding pair is between the two atoms. So BP bonding pair, they go between the two atoms. So you have lone pairs and bonding pairs. And when you say a lone pair, it is assumed to be two electrons. If you say lone pair electrons, then that is just the one. But lone pairs, two electrons, bonding pair, two electrons. When you are drawing these 2D Lewis structures, the very first thing you want to do is sum the valence electrons. And that is going to be for all of the atoms in the molecule. It's all of the atoms that are in that molecule. Once you have the sum, you're going to bond everything to the central atom. I call this making the skeleton. Now, your central atom is usually the first element in a binary compound. So a binary compound or a binary molecule, if you will, is going to be something that only has two elements in it. And it's usually the first, but keep in mind it can never be hydrogen. Hydrogen can never be the central atom. Another way you can look at is it is going to be the least electronegative atom. And again, never hydrogen. Hydrogen cannot be a central atom because it can only hold two electrons around it. So it can really only have one bond. Now, after you bond everything to the central atom, you draw a line between the central atom and all of the other atoms, you're going to subtract the bonding electrons from the valence electrons. And then as soon as you get that number, you're going to distribute the remaining electrons around the outer atoms first, and then the central atom if it is needed. Sometimes it's just not needed. You can get rid of all of your electrons by just putting them on the outer atoms. The next thing you want to do is check the octet rule. All right. Remember, the octet rule is 8 electrons around each atom. Now, we can also have the duet rule. For small atoms, they're fine with only 2 electrons around it. So 8 electrons on each atom or 2 electrons if they are going to fulfill the duet rule. And then you can form double or triple bonds if the octet rule or the duet rule is not fulfilled. So if you get to step 5 and everything looks good, just stop. You don't have to do step 6. If you get to step 5 and the octet rule is not fulfilled, then you can move on to step 6. Let's get some practice. Draw the Lewis structure of CH4. So the first thing I want to do is sum the valence electrons. Carbon has 4 valence electrons, and there is 1 carbon atom. So that's going to be 4 valence electrons from the carbons. Hydrogen has 1 valence electron, and there are 4 hydrogens. So we're going to get 4 valence electrons from the hydrogen, which means we're going to have a total of 8 valence electrons. What this means is my Lewis structure has to have 8 electrons because those are the electrons that are going to be responsible for bonding. Those are the electrons that can be shared. I can't do any more than that. I can't do any less than that. My next step is to draw the skeleton. So carbon is going to be my central atom. I know hydrogen can't be the central atom, so carbon is a good place to go because there are no other atoms. And then I'm going to draw my 4 hydrogen atoms around my carbon and bond them to the central atom. I drew 4 bonds, and there are 2 electrons in each bond. So that is going to give me a total of 8 electrons. So I started with 8 valence electrons, and I just drew 8 bonds. So we're going to subtract 8 bonding electrons, and that's going to take me to 0. So I don't have to distribute any lone pair electrons because I don't have any electrons to do that with. There's no electrons left. Also, I cannot put any more hydrogen or any more electrons on hydrogen because it already has the 2 electrons around it and it can't hold any more. Now I can check my octets. All of my hydrogens look the exact same, meaning that they all have 1 bond coming out from it, which means that the duet rule is fulfilled because hydrogen is fine with 2 electrons. Now, carbon has 4 bonds to it, and there are 2 electrons in each bond, so a total of 8 electrons, and the octet rule for carbon is fulfilled. Let's look at SiO2. Silicon has 4 valence electrons. Oxygen has 6 valence electrons, and there are 2 oxygens. So we're going to have a total of 16 valence electrons. Silicon is going to be my central atom. It is the first atom listed, and also it is less electronegative than oxygen. So silicon is going to go in the middle, and I'm going to put oxygen on either side. Now I'm going to make 1 bond between the silicon and each oxygen, and that is going to account for 4 bonding electrons, which means I have 12 valence electrons left over. I need to distribute those electrons and put them in my Lewis structure. Now remember, we're going to put them around my outer atoms first, so I can fit 6 around this oxygen, 6 around this oxygen, and I have accounted for 12 more electrons. So I'm going to subtract 12 lone pair electrons to give me a total of 0. Notice that these are lone pair electrons. So there are 12 lone pair electrons, or you can say there are 6 lone pairs. My next step is to check the octet rule. The oxygens, they have 3 lone pairs, so that's 6 electrons in the lone pair, and 1 bond for another 2 electrons. So I have 8 electrons around each oxygen. Notice the oxygens look the same in the sense that they have 6 lone pair electrons and 1 bond for a total of 8 electrons. Now, silicon is not happy. Wah, wah. It only has 4 electrons around it. I have 2 electrons on this bond, 2 electrons on this bond. So I need to form double bonds in order to fulfill the octet. So what I can do is I can take a lone pair and dump them into this bond here to form a double bond. And notice that when I do this, I have not changed the number of electrons around oxygen. I have 2 lone pair electrons for a total of 4 electrons. And now I have 2 bonds for a total of 4 electrons. So together we still have our 8 electrons. So the octet rule of oxygen is still fulfilled. And now I've changed the electrons around silicon to 6. I can do the same thing on the other side. Take that lone pair, make a double bond, and now I have fulfilled the octet rule for all of my atoms in my Lewis structure. So this would be the correct Lewis structure. It does not matter to me how you write your lone pairs. You can have them here. That's just fine. You do need to make them a pair though. So we cannot write our lone pairs, 1 electron here and 1 electron here. These are no longer lone pairs, they're free radicals. So Si2 does not have any radicals, so that means I have to write them as lone pairs. All right, let's look at one more example. Hydrogen has 1 valence electron, carbon has 4, and nitrogen has 5, so we have a total of 10 valence electrons. Hydrogen is the least electronegative atom out of these 3. However, hydrogen can never be the central atom. So that means carbon has to be my central atom. And I can draw hydrogen on one side, nitrogen on one side, and bond them to my central atom. I made 2 bonds, so this is going to account for 4 bonding electrons. I have 6 valence electrons to work with. I want you to be careful on this one because I cannot put any more electrons on my hydrogen. That just doesn't work because I can only have 2 electrons around hydrogen. So that means all 6 of the electrons I have left over are going to go on the nitrogen. And since I drew 6 lone pair electrons, I have accounted for all of the electrons in my structure. Now I can look at the octet rule. Hydrogen is fine because it has 2 electrons on it, around it, so it fulfills the duet rule. Nitrogen is fine because it has 8 electrons around it. The issue comes with carbon. Now I cannot just start adding electrons because now I'm dealing with 12 electrons when I only have 10 to work with. Another thing about this is I now have 10 electrons around nitrogen, so I can't just start drawing lines. I need to shift my electrons within the structure around. So the lone pair from nitrogen can donate and form a double bond between the nitrogen and carbon. Notice I still have 8 electrons around nitrogen and the octet rule is fulfilled. The octet rule is not fulfilled for carbon, so I need to keep working with this. I want you to notice that hydrogen doesn't have any lone pairs to work with, so I'm not going to be able to share any more electrons from the hydrogen. However, I can take another pair from nitrogen, and now I can form a triple bond. So this is going to be a Lewis structure, the Lewis structure for HCN, hydrocyanic acid. Go ahead and try the following Lewis structures on your own. You can ask me if you have questions. Let's look at bond polarity. I want to look at the example SiO2, and we just drew this one, so this will be a good one to check out. When I look at the delta En between Si and O, oxygen has an electronegativity of 3.5 and silicon has an electronegativity of 1.8. So this is going to give us a difference in electronegativity that is 1.7. If we remember, this goes into the polar category, but I cannot explicitly state that SiO2 is a polar molecule. I can say that the bond between silicon and oxygen is polar, but I can't say what that the whole molecule is polar. So let's draw our Lewis structure for SiO2 again. We already drew it, and it looks like this. My difference in electronegativity is indicating that I have polar bonds. So I can draw a dipole moment from the silicon to the oxygen, which makes the oxygen partially negative and my silicon partially positive. Well, the same thing is going to happen in the other direction as well. So both of my oxygens are going to be partially negative. Now, what happens is we have to add these dipoles together. And I want you to remember that this is in the 2D only. And this example is a little bit easier to see because it is a linear molecule. It exists only in the 2D. But you can think of it as the dipole moment is going in the plus 1.7 or the plus 1.7 direction and the minus 1.7 direction. What happens when you add these two together? Yeah, we get 0. So yes, this molecule has polar bonds, but as a molecule, it is a non-polar molecule. And that is because the dipole moments are in equal and opposite directions. So the dipole moments cancel out. The dipole moments are in equal and opposite directions. Let's check out another example. We can look at H2O. First thing I want to do is sum up my valence electrons. Hydrogen has one valence electron, and there are two hydrogens, and oxygen has 6 valence electrons. So I'm going to have a total of 8 valence electrons to work with. Oxygen has to be my central atom because hydrogen cannot be. So I'm going to distribute the hydrogens around my oxygen and draw a line between them. So since I drew 2 lines, that's going to account for 4 bonding electrons. So I'm going to have 4 valence electrons left over. I hope you can see that if I distribute the electrons around my outer atom first, I'm not going to be able to distribute any of them because hydrogen cannot hold any more electrons. So that means I have to go to my central atom. I can already tell that the delta En for hydrogen and oxygen is going to be polar because there's a large difference in electronegativity. So I know there is going to be a dipole moment going from the hydrogen to the oxygen, and then it's going to be going from the other hydrogen to the oxygen as well. If I draw it in this way, it looks like they are equal and opposite. However, molecules don't exist in the 2D. They exist in the 3D. So this is not the actual shape of water. Anytime you have a lone pair on your central atom, it's also going to change the dipole moments. And that is because there is kind of an extreme dipole moment between oxygen and the electrons because the electrons are not partially negative, they just are negative. So when I put all of those four together, they're not going to cancel out. So that means this is a polar molecule. And that's because the dipole moments do not cancel out. So there's kind of two things you can look at. So if all of the outer atoms are the same, you're going to have a non-polar molecule. If all of the outer atoms are not the same, then it's going to be polar if there are polar bonds present. If there's no polar bonds present, then it's not going to be polar. If the central atom has a lone pair or multiple lone pairs, then it's going to be a polar molecule. Even if you don't have polar bonds in your molecule, you're still going to have a polar molecule because of the lone pairs.